All right, kicking off with question 1. We have a significance test right off the bat. We know that because it asks significance level and then do the data provides convincing statistical evidence. And it gives us proportions. We've got 2 proportions coming from 2 separate samples. And this one's going to be 2-sided. This is a 2-sided test. And we know that because it's asking if there's evidence of a difference in the proportions. It doesn't say whether they think one is bigger than the other for how much are interested in the online fitness classes. It's just asking, is there a difference, not in any specific direction. So because of that, our null hypothesis is that the difference is 0, and our alternative is that the difference is not 0, or that null is P1 equals P2, and the alternative is that P1 is not P2. And then we make sure we define our parameters here, that P1 is the proportion 18 to 55, and then P2 is 66 or 56 or older. And you can do that either way. You just need to make sure you define which one is P1 and which one is P2. Then I also went ahead and put in what P hat is for P hat 1 and P hat 2. Then we're doing a 2-proportion Z test, or a 2-sample Z test for proportions. And then our conditions there are random, normal, and independent. So for random, we have to check both samples, separate random sample. And then for normal, we check n times P and n times 1 minus P hat for both samples. And they're all at least 10, so we have a normal approximation. And then for independent, take our sample sizes, multiply them by 10, and we say that there are at least that many members at the exercise center in those age brackets. Again, we check each of those for both samples. Then we need, in order to do our formula, we need our pooled proportion. Our pooled proportion here is we treat it as, if the proportions are the same, we can treat it as one big sample of 400, that's over here. And out of the total of 400, 130 of them were interested in the class. So that is our pooled proportion. Then we put in for our Z-score. So again, we do our 2-proportion Z test in the calculator, and that will also tell us that negative 0.92 is our Z-score, and our p-value is 0.3587. Make sure that on the denominator here, you're using p hat sub c in those standard deviations. That p-value, 0.3587, is greater than the alpha level they gave us in the problem of 0.05. So we're going to fail to reject the null hypothesis, which means there's not enough evidence for the alternative. And the alternative in this case was that there was a difference in the interest between the age groups of taking the online class. So we failed to reject, not enough evidence for the alternative. That was question 1. On to question 2. Question 2 was our question about the water bottles at the different schools. So it asked for us to make the relative frequency charts and gave you a key to work with. And if you'll forgive my scale, here's roughly what your segmented bar chart should have looked like. And then part B asked, and we, by the way, this was 0.5, then 0.3, then 0.2. 0.5 here, 0.3 here, 0.2 here. And then the same, it said that the middle school was the same throughout. So a third, a third, a third in each of those. So your bars should have been roughly equal in length. Then in part B, it says the elementary school thinks that they sold more small bottles than the middle school did. Well, based on this chart, you might think, well, that small sure looks like a bigger slice than the middle school, but that is misleading because the proportion is greater at the elementary school, but that doesn't account for the large sample of the middle school, the large amount of water bottles that the middle school sold. So therefore, we can actually calculate this. So you can use a number here, but I just use X to stand for how many bottles the elementary school sold. If the elementary school sold X bottles, then half of that X was the small water bottles. The middle school, therefore, if the elementary sold X water bottles, the middle school sold 3 times that, so 3X bottles, and a third of those were small, and so a third of 3X is just X, which is more than the 0.5X that we saw earlier. Then for part C, it gives you the mosaic plot and asks which sold a greater proportion and which sold a greater number. So for the greater proportion, you can see that this one has a little bit of a higher, goes up to a greater height for the large for high school A than for B. But you'll see that in the mosaic plot, this width is standing kind of for the sample size. And so you can say that A sold the greater proportion, but B sold a greater number. And in the plot, you can tell that because of the height for the proportion and because of the area for the total number. So that's your process on question 2. Question 3. We have our car maker. We want to look at which model has the best mileage. It's asking, is this an observational study or an experiment? Well, it's an observational study because the owners are not being randomly assigned to any particular model. Make sure you include context here. Don't just say observational study because there is no treatment. You want to include that context. Why is there no treatment? Well, there's no treatment because the owners are not being randomly assigned to the model. They're just being asked, what model car do you drive? And then go from there. So there's no treatments happening. Then for part B, we have someone who has model D. And so we're going to do a completely randomized design. So first off, for the days, we're going to pick 35 of the days at random. That means that we need to assign each day a number 1 to 70, or if you used a table, you need 0, 1 to 70. Then we're going to use our random process to randomly select 35 days. And those methods can include using random INT or random number table, or my favorite is putting slips of paper in a hat. But however you choose, you want to make sure that every one group of 35 has an equal chance of happening. So you're randomly selecting those 35 days, and then you want to say what's happening to them. So those 35 are going to be the ones that use the autopilot, and then the other 35 will not. So you want to say which one is which and which one you're going to. The next part, we're a member of the Model D club with thousands of members who all drive this model of car. Therefore, we want to generalize these results to the population. In order to do that, we would need to take a larger sample to account for other variables that might be in play. Just one car driving on one stretch of road is not enough. And then I went ahead and gave some examples of why that might be important. For example, that car might be particularly well built. The autopilot feature might be really, really good in that car and then not so good in other cars. Or he drove on the same route every single time, and so that route might be really well geared to that autopilot feature, whereas other people driving on other routes to work might not have as good a time with it. So we need a larger sample. That's the idea of replication in our experimental design, is replication, doing this a repeated number of times. On to question 4. Question 4 is your question that's focused on probability and focused in this case on geometric distributions. So we are opening geodes until a red crystal is found, and each outcome is independent, so the probability stays the same of 0.08 every single time. So I started by going ahead and phrasing and saying what distribution this had. So let S be the number of geodes that Sarah needs to open. Then S is a geometric distribution, and geometric just has the one parameter of P. The probability of the thing happening is 0.08. So what's the mean and what's the standard deviation? Well, you can find these. These are actually on your formula sheet. Sorry, wrong way. These are on your formula sheet. So we can go up to the formulas here, and you can see that with a geometric distribution, our mean is 1 over P, and then our standard deviation is the square root of 1 minus P over P. So we're just going to plug our value of P of 0.08 into that formula and plug 0.08 into the standard deviation formula, and there they are. Then in part B, this is what the filled out table should look like. So that's your probability of 3 and probability of 4. To get the probability of 3, that probability of 3 only happens when the third one that we open is a geode. Because we go until we get the red crystal or until we hit 4 and we stop, whichever happens first. So if we stopped at 3, that must have mean that we got our red rare geode. So that meant the first 2 were not the red, and the last one was. So we had not a red, not a red, red. So the probability of not a red is 1 minus the 0.08. That's the 0.92. So not a red, red gives us 0.0677. Then for 4, there's 2 different ways you could get 4, which is either that that last one was a red, or that we're just stopping after 4. Well, that's going to happen either way. We're going to stop after 4, regardless of whether we got the red or not. So it doesn't matter what the fourth one is. It only matters that the first 3 were not red. So 0.92 times 0.92 times 0.92. Not a red, not a red, not a red. And then we'll stop after the fourth, regardless of what the fourth is. Now, Conrad may care about whether we got the red, but we don't for this probability. The other way you can do it is, since you have the other values in the table, this should be all the possibilities. This is the entire sample space, so this should all add up to 1. So we can take 1 minus the rest of the probabilities we found, and we get the same answer. Those are kind of the 2 main approaches that you can use to think about it. Then over in part C, they want you to calculate the mean of the distribution, and in the second section to interpret that mean. So to get our mean, since we have the table, it's the value times probability of it happening, and we're going to add them all together. That's 3.545. And here's your interpretation of that expected value. The 2 key things you want to have in this interpretation is to make sure you talk about this happening in the long run. So I say a large number of times. And then this is what happens on average, right? It's a mean. So it's happening on average in the long run. It's not on any one particular time. In fact, it's possible to open things 3.545 times. It's in the long run on average. Those are the things you want to make sure that you mention. All right, question 5. This one had a little bit of everything. It's your multi-focus question. So first of all, we have some probabilities that we're calculating off of this table. Collector is selected at random. So one collector selected at random, so that is out of the entire sample that we took, which is our 500. Out of that 500, how many of them had 11 plus months? So we need to combine, here's all of the 11 plus months and having the regular. So we're gonna pool all those together and get 259 out of those 500, which is how we get our 0.518. Then part B is a conditional probability. Given that a collector has been collecting for fewer than 6 months, what is the probability that majority regular? So it is out of this amount right here, out of the 91 that have fewer than 6 months. How many of them are regular? Well, 80 of the 91. Vast majority of them, of those small collections. Then for part C, we go on to the significance test. Believes there's a relationship or association between the number of months and which type. So since we got categorical data in a two-way table, we should be looking at a chi-square test. And this is a chi-square test of association or chi-square test of independence. So null hypothesis is that there's no association between how long we've been collecting the cards and their amount, the amount that are rare. And then the alternative is that there is an association between duration and rarity. And then in part D, they give you a p-value. And we're assuming the conditions are met, which they are, by the way. What conclusion should they make about the belief? Well, that p-value, we get a chance at writing our rejection sentence. P-value is less than our significance level. Any reasonable significance level, 0.05 or 0.01. We're going to reject the null hypothesis, which means there is enough evidence of an association between duration and rarity. Finally, we have question 6. And I've always given the advice of kind of skim throughout the question to kind of see where they're going with this. And if you do that, the broad idea of where they're going with this question is to talk about the normality condition when our sample size is less than 30. So we've kind of had this vague sense of when n is less than 30, then we look for, as the question later says, not strongly skewed and doesn't have outliers. That's what we're looking for. And so we're going to have a clearer definition of that we developed throughout this problem. So we start in our familiar territory here. We talk about what is the inference procedure to use. And because we want to estimate what the mean is, what's going to let us provide an estimate for it is going to be a confidence interval. So we are here doing a one sample t interval for a mean. And what is that mean? That's what it asks here, the parameter. It's the mean price of this type of whistle for all stores. It basically lays that out in the question. Just making sure you can define the parameter and know what a parameter is. Then in part B, we're still relatively in familiar territory. Part B, we have this dot plot and then summary statistics. It asks us to describe the shape of the distribution. And we're going to justify response using the summary statistics. So for this shape, we're going to say that this shape is slightly skewed to the right. And we're going to say that because if you look at these summary statistics, our mean of 5.12 is greater than our median, which tells us that our mean, is getting pulled slightly to the right by this skewness. You can also use other things like, the distance between the minimum kind of Q1 and the median and how those are spaced, and then how the median, Q3, and the maximum are spaced a little bit slightly further apart. That's also a little bit of an indication of the skewness, but mean is higher than the median is what I went with there. And then we wanted to use our 1.5 times IQR rule in order to test for outliers. So there's our IQR. And 1.5 times IQR, we take third quartile minus first quartile. Then we're going to multiply that by 1.5. Subtract it from the first quartile and add it to the third quartile. And if we look at our table with our minimum and our maximum is 4.25 and our maximum is 6.58. So all the data is within the boundaries of those fences. So we conclude that there are no outliers because all the values are in between those two boundaries that we found. All right, so far, familiar territory. Now here's where question 6 throws in the twist. They give you a new formula and statistic that you have not seen before, and see what you can do to work with it and how we interpret it. So first off, they give you the formula. We have x bar minus m over s, and sample mean, sample median, and sample standard deviation. Luckily, all those values are right up here in the table that we did earlier. So the first part of this is we can just plug it in. Plug in our value. Here's our mean, here's our median, here's our standard deviation, and we get 0.9489. So I've provided a rough sketch of about where it is, but 0.9489 is our value, so that's about here. And then the sample size is 20, that's about here. So therefore, we put our x right around there. And you'll notice that that's in the considered strongly skewed category, but not very far outside of the approximately symmetric category. So in the skewed category, but not incredibly so. And you'll notice some ideas that we've talked about before in the class. For example, the larger the sample size, the less we have of a skewed distribution, those kind of things. So then we go down to say, would we conclude the shape of what would we conclude about the shape? Well, we're backing up what we said earlier about the data being skewed. And that's going to lead us finally to talk about the normality condition, which is laid out here. When the sample size is less than 30, we need to make sure that the data is not strongly skewed. Well, bad news. Our sample size is less than 30 and there's no outliers. We already tested for outliers earlier and said there were no outliers, but we do have a skewed distribution as we just calculated and concluded. Therefore, we say that that normality condition is not met. So again, that's our broad idea about the normality condition and how it relates to when n is less than 30, how can we potentially check for that skewness? And those are your 2024 questions.